a number of patents, and this startup company that I'm going to talk about. And it's been just an incredible experience. And I think when it comes to having these kinds of interactions with a person from different field, the best way to do it is if you're actually friends, because it makes things a lot easier. Of course, it challenges your friendship at times, but if you're moving in the same direction, I think at the end it's going to be beneficial. So this technology that I'm going to talk about really started off when one of my postdocs, along with Bob Langer's postdoc, Akhilesh Kaharwar, came to the lab. He's now a professor at Texas A&M, and he really introduced us to these class of materials that are silicate-based nanoparticles that have very interesting rheological properties. Based on some of this work, we started to build up on a family of materials that we created some intellectual property for. We started working with Rami and published a seminal paper in Science Translational Medicine, and we got more intellectual property and a couple major R01 grants that demonstrated its importance in the scientific field. And Obsidio was founded late in 2018, and over the past year and a half, 2 years, we've been working on developing a number of different advances to it, including a couple funding rounds as well as some SBIR grants. So what exactly is this thing? So the material that we've been developing is a combination of a couple of components. One is gelatin, which is very abundant in tissues and different medical devices, combined with laponite. And these laponite is a form of nanosilicate, which is very small particles that are disc-shaped, and they have also asymmetry in their charges. As you can see on the edges, they're positively charged, and in their flat sides, they're negatively charged. And based on these charge distributions, they can interact with themselves as well as with the polymers, and create a material that is shear thinning. That means that if you apply force to it, it actually flows. And when you remove the force, it stops flowing. So this allows you to have these toothpaste-like properties, so that you can deliver it through a needle or a catheter, but once it comes out, it maintains its shape. So I don't know if this video is going to work with sound.
No sound.
Okay. All right. So basically, what it talks about is that in embolization, it's basically a procedure that basically allows you to go inside the blood vessel and block it. And this can be used for tumors, to be able to starve tumors from oxygen by blocking their blood supply, as well as other areas. So this is really what embolization is about. Now, embolization is used in many different applications. So tumors is one of them, where you can take tumors and basically block off their blood vessels. It's also used in the brain to be able to address things related to aneurysms in the brain, as well as other types of bleeding that occurs in the brain. And finally, it's used in peripheral vasculature. So for many different applications, when you need to, again, plug blood vessels, fill them, and be able to deal with it. So this is really what embolization is about. And if you think about this process, what's typically done is as follows. So this is an example of an aneurysm. So what interventional radiologists do is that they go in with a catheter, and then they kind of fill this aneurysm with these wires. Now, the wires have been used for a number of decades, and what they do is that they basically slow the flow of the blood inside the area, and it causes the blood to stop and form a blood clot. So that's what happens. And but it doesn't work all the time. So this is an example. You see here is the guide wire for this catheter, and you can see that through it, lots of different coils have been deposited. But in this case, actually, it didn't really work. All these coils together did not stop the bleeding. And this is the kind of stuff that happens. So here you see, again, lots of these coils. And then once you put contrast upstream, you see that it goes directly through this, as you can see by this contrast coming downstream from here. So this basically shows that it doesn't work in every case. And the reason it doesn't work, and in this case, it's a gastrointestinal bleeding that occurs, so you see the bleeding continue. The reason it doesn't occur is that many people actually have impaired ability to form blood clots. So if you're gone into an accident and you've lost a lot of blood already, you can't form blood clots as easily. If you've are under treatments for blood thinning, so people who are on warfarin, for example, they can't form blood clots as easily. So in all of these cases, these procedures cause very high complications rates. So based on this problem that Rami presented, we came up with this material, which is, as I mentioned, combination of these two components, and we came up with a family of different materials based on changing the ratio of these two different components. And we basically identified as nanoclay with NC with percentage of this nanoclay. So you can either change the ratio of these two components, or you can change the concentration of the whole solid component in the liquid. And based on that, you can start getting different types of materials. So these materials
Ali, we can't hear you.
Hello. Hi, guys. Am I still connected?
Now you're
Sorry.
connected.
All
Yeah,
right. Sorry
we can
about
hear
that.
you, but we can't see your camera.
Oh, you can't see. Okay, so let me redo the sharing.
Sure.
Sorry about that. I was on a VPN for my day job, and it just kicked me off. So I will come back on.
This usually happens to me a lot when I'm at home.
That's right.
Yeah.
So 1 second, and all right, now I can share. Do you see it now, actually, or not yet?
Not yet.
Okay. So stop sharing and show.
There you go. Awesome.
Well, that's me. Hold on. Show entrepreneurship. Okay. And boom. Wonderful. Now it's, oh, white screen?
No, it's your previous slide, but it's frozen.
All right. So let me. All right, show again. And oh. All right, so you guys don't see this?
No.
All right.